Right, today we're going to do more with solving trig equations. The first two questions just ask you to preview questions 1 through 6 and take a look at how they're a little bit different than last time. I'd like you to pause the video and answer just those two questions for me. We're actually going to do 1 through 6 together after that. Okay, so try that for me, please. Hopefully you notice that all of these values that we're working with, or all these equations, have a value in front of the x or the theta inside. And from last chapter, that indicates that we have a period change. What that's going to do when we're finding solutions is, one, if we're solving this algebraically, it would add another step. We have to get rid of that too. But what we're going to also talk about is how it affects generalizing the solutions. They recall from last time we have theta equals, or in this case it'd be x, but we have some number and then we generalize using the period. If our period is changed, we can't just use that 2 pi n anymore. Okay, so we're going to do this first one kind of as a review of last time. We'll do it algebraically and then talk about those changes. So if this 2 weren't there, we would draw this in quadrant 2 and quadrant 3, because that's where cosine can be a -1/2. And in this case, it's one of our nice triangles because we're used to seeing 1/2 on our special right triangle of 30, 60, 90. And if the 1/2 is there, that's a 60-degree angle here. What's different is what we just did is we really did the inverse cosine. And remember, with your inverse cosine, your calculator gives you one answer, and it's going to give you that one in quadrant 2 because the restriction is from 0 to pi. So it gives us one of them, but we really have to talk about 2 of them. Now, the reason I brought up inverse cosine is because that cancels out the cosine, okay, and it simplifies this to our angle, and we're really saying that 2x, because that 2 really is there, could be this first angle that we know as 120 degrees, or we could think about it as the second angle. We talked about cosine is easy to go counterclockwise and clockwise to get the 2 answers. So we could also say 2x is -120 degrees. And from there, our last extra step is that the angles themselves are x equals 60 degrees and -60 degrees. Just like before, we want to generalize with radians instead of degrees. So this would be pi over 3, and this would be -pi over 3. But our period change is what we have to pay attention to for these. Normally, my period for cosine is 2 pi, but from last chapter, a 2 in front is a horizontal compression, so we've got to multiply that by 1/2. So really, we've got pi that we're tacking on, not because they're diagonal from each other, but because our period change means we're really not on this unit circle anymore. Okay, but this wasn't so bad only because it was one of our nice triangles. We want to talk about how we can do this process a different way. So today's focus is actually going to be graphing to solve instead of doing it algebraically. So this is option 1, but there is another option when we see a period change that makes our life a little bit more challenging while solving. In order for us to graph, we want to make sure that we are graphing in degrees. This whole chapter's been in degrees, so we want to do that. And remember from last unit, when we were graphing our equations, y1 and y2, and looking at intersections, we wanted to make sure our window was appropriate so we could see the all the values of those intersections. There are going to be a couple changes that we're going to work on. One of the changes is obviously that we're going to have our mode in degrees versus radians, which means when we think about our scale or our window, we're going to make sure that this applies to one period in degrees rather than one period in radians. So for us, that would mean we're going to go 0, not to 2 pi, but to pi in terms of degrees, which is 180. And then for this, to kind of make our life easier so we don't have to do too much adjustment with our window when it comes to vertical scale, is we're actually going to, instead of using y1 and y2 as is, it's going to make our life a little bit easier if we get this whole equation equal to 0. So that'll look like cosine 2x, and we can add that 1/2 over to get it equal to 0. This will be our y1, this will be our y2, and then when we think about our range or our y values, the only thing that's going to change our -1 to +1 is if I have a shift or a stretch in the front. And so we're going to generally start off with a -2 to +2 to give some extra space. And as long as we're not seeing anything too crazy going on here, we should be able to leave that. Okay, so let's take a look. Okay, so in your y equals, we can clear out anything that's in there and type this equation, cosine 2x, and then plus the 1/2. And then we'll go adjust our window just like we talked about. So 0 to 180. An x scale is really anything that goes into your period evenly. So maybe 30 for this one. And then we decided -2 to +2. Okay, we did this so that we would see one period or one lap, and from cosine, max to max is showing up, so that's good news for us. If you ever have an issue where your graph looks really chaotic or like a flat line, the things you want to check is your mode, that it's in degrees, and that you have chosen an appropriate window based off of the period. Again, the period in degrees. All right, so looking at this, our intersections are where our solutions are. You can second trace intersection to find those. And we've got 120. We'll come back to what that represents. And then the second one, we get over closer to it. You don't have to be right on top of it. You just have to be over halfway. Is our 60, which matches up with this. And I said I'd come back to this, the 120, because if we go back to our original graph, this whole thing, we decided 120 was easier, but we could have gone this direction as well to get to the point, which would have made this 180 plus 60 is 240 degrees. And then we divide that by 2, it really is 120. So that is going to give us the positive versions in the first period when we're dealing with our graph always. Okay, so looking at number 2, we see an a value here again. We have a number in front of our variable, which indicates that graphing is going to save us that extra step. And so we'll do this one the same way. Okay, so starting out, we're going to find the period that would be appropriate in order to be able to graph this. So normally we have 2 pi as the period. This is a horizontal stretch, so we multiply by the reciprocal for 6 pi, which is the same thing as 1080 degrees. A reminder, you can convert to degrees by just multiplying. Instead of pi there, you can replace it with 180. In this case, you could take 360 times 3, 360 with whatever you're doing on the inside of that parenthesis. Just like last time, we're going to get this thing equal to 0. So when you add that over, we get sine 1/3 theta equals 0. So our y1, y2. And then our window is going to be chosen based on this and anything in the function that may affect our scale. Since there's nothing in front or added, a -2 to 2 is going to be just fine. Taking care of that, we've got sine of 1/3. X is just fine. And then our 0 is already in there. We just have to adjust our window. .30 is a little bit small of a scale. It does go in evenly. If you want to cut it down any to count by, you could use 90 or 180, and that might make it look just a little bit nicer. Another thing choosing a scale helps with is recognizing nice values. These are hitting right at those tick marks, so you can count 1, 2, 3, 4, 5, 6 times 90 is 540 without having to actually trace them. Although when you hit that, you can see that it really is at 540. We are seeing an intersection at the beginning and the end as well. So we've got 0 degrees, we've got 540 degrees, and we know our end is at 1080. Okay. What I want to talk about for a minute here is the 0 with the 180. If we go back to unit circle, this point can be written multiple different ways, just like any other value. But we always label this as 0 or 2 pi. First lap was 0, and then going around is 2 pi. The same type of idea is happening with the graph itself. This is sine, so I'll use sine here. Okay, here and here, I could call this 0, or I could call it 2 pi, but the sine value, the y value of that graph, is exactly the same. When we talk about a graph that starts at the intersection, the first and the last are the same value, just another lap later or another period later for us. From 0, 1080 later is 1080 itself. You never need both the first and the last. Okay? Now, we're going to still change these to radians. 0 is still 0. 540 is 3 pi. And oftentimes when we're graphing, if there are only two solutions, I'm not going to have you worry about trying to come up with a pattern. Sometimes on our unit circle, we decided that if they're diagonal from each other, there's a constant pattern, so we can generalize those a little bit better than just adding the period. When there are just two answers, I don't want you to necessarily worry about that. But I will show you on here something that I see, because we do have those three numbers, is from here to here, we've got 540. And again, there's 540. And because we had three numbers to start with, you can determine a pattern from there, which means you could actually group these together a little nicer and say the first solution is at 0, and then they happen every 540 after that. We already decided that 540 is 3 pi, so we can write it as 3 pi n, where n is an integer. If we just have two, so suppose there were not all three in this window, then what we would want to do is stack them separately, just like we have been doing, and we would add the period on, which from earlier was 6 pi rather than 2 pi. Okay, so we're going to see that as we practice through some more problems here. Okay, looking at the next one, we did do some quadratics last time where we had a squared sine or cosine term, but again, this one has a coefficient in front of the variable, which means we're going to go ahead and graph to solve these ones as well. Okay, so just in your calculator is fine. We're going to move some stuff around. We want all of this to the other side, so 2 cosine. You'll notice it doesn't let you put that squared there. You're going to have to put your 3x, close it, and then square it, minus cosine 3x, close it, and then subtracting that 1 over. Okay. Going to our window, this is something I would recommend writing down as your period, is you're taking our 360 or our 2 pi, and we're dividing it by 3. Okay, so 360 divided by 3 is 120 for our x maximum. Change this back to 30, so it counts by something not so large. And then here, negative 2 to 2 is probably okay. It may not be. This 2, remember, deals with our amplitude change, and then we are shifting it down 1, so we may have to adjust, but we'll start with this to begin. Okay. So in this case, we do see an amplitude, kind of a mixed bag here, and so I'm going to talk about how this shape is very unique to what we've seen. Obviously, we're not coming all the way back up to the maximum. We can't see it in this graph. So I'm going to extend my window. You don't need to do this. I just want you to watch. If I change this to 240, that would graph 2 periods for me, so we can see the pattern that's happening. So here we can really see that that little maximum point here, it's not going all the way up like we would expect with a regular cosine graph. This kind of goes back to what we did in chapter 1. Anytime we have two functions put together, like we saw a quadratic put together with a square root function, and it made a graph that either looked like a semicircle or ended up looking kind of crazy going in both directions with those square roots. Anytime you put two functions together, there's no guarantee it's going to look like one of the original functions. The same thing is kind of happening here. When you combine sine waves, you're not going to necessarily see a consistent maximum and minimum all the way through. Okay? So we've got a cosine times a cosine, and then we're subtracting another. So we're doing a lot with these functions, which is going to affect your shape. So with our shape, it kind of looks like this cowboy hat shape, but it was really one lap. So I'm going to go back to the original window, and in our one lap, we're going to talk about solutions just like we have been. So it looks like 1, 2, 3, 4 in this window. But remember, if it starts at 0, you don't need both the first and the last. You just need one of them. And we'll just go find those. Okay, so I know 0 is happening. And I know 120 is happening just based off my window. Make sure you save yourself time with that one. And then we just go trace the other ones. So first one's at 40 degrees. Do that again. Get a little closer to the other one is all you need. And that one is at a nice 80 degrees. Okay, we do have more than 2 answers here, which means we can look for a pattern if there is one. And so here we've got adding 40, adding 40, adding 40. There is a pattern, which means I just need to start somewhere. In our case, it's 0 radians. And then we have to add 40 to that, but we want it in radians. So just like we have been doing, divide by 180, tack on a pi, and we've got 2/9 pi for our pattern, where n is an integer. Now I will tell you when you look at my key, if you're checking your answers, you're not going to see me write this 0 plus. I'll just have 2 pi n over 9, because when we say 0 plus anything, it's just the anything. So I've simplified on some of these. It doesn't bother me if you write it, because that just shows me you are starting at some number and then adding some constant pattern after that. Okay, on the next one, I want you to actually pause the video and choose a window for me, and then we'll talk about it all together. Okay, for this one, I'm not sure if you noticed with your equation or not, but there was a 2 theta in one parenthesis, and the other one just had a regular theta. That indicates that with our first piece of our equation, the period seems to be pi, but with the second part of our function, the period appears to be 2 pi, or regular 360. When that's the case, when these two don't agree on what the period should be, we're going to have to check both. So this one says it's supposed to be pi. This one says it's supposed to be 2 pi. We're going to start with the larger one, 360, and see if that shows a full lap or 2 full laps. Okay. You may have skipped over this -2 to 2 and not be able to see the whole thing. Okay, that's going to be important for us to decide which one is actually the period is adjusting our window. But we can't see the whole thing because really of these things that are happening. We've got this 3 and this 5, and because of that, our maximum and minimums are outside of our range. So we're going to have to choose something larger, maybe -8 to 8. You could do a nice -10 to 10. It just adds a little extra space where we can see the whole thing. Okay, so at least bigger than your largest coefficient. From here, this 360 is just one period. It's not 2. Because if I split it in half, I'm seeing only half of this lap. I'm not seeing the whole thing. Okay, again, if you're worried that maybe you don't have a big enough window, you can always double that value to see the repeat happen, especially when we get into these very strange new types of graphs. Okay, so we have 2 solutions in the first period, and those are the 2 that we need to find. Okay, so if you watch your scale, like my scale I changed to 60, but yours may still be at 30. This says 60, 120. Okay, I can trace 120 to check it, and it's there. And so then this one would be 240, and it does work. So we've got 120 degrees, 240 degrees. And this goes back to what I was talking about on the first one. There's no such thing as a pattern between two numbers. Because I could say this is plus 120, but I could also say the pattern is times 2. You have to have at least 3 numbers to determine a pattern. And I'll go back one more time to this larger window just to convince you that there's no necessarily equal distance between these two and the next one. Because if this was 120, we should have had a solution at 0, and that wasn't happening on our graph. Additionally, if you extend this out, we've got this shorter distance here, and then there's a big gap till the next one. Okay, so when there's only 2, you're going to stack them on top of each other. In radians, that'd be 2 pi over 3, plus our period, we decided the winner was this one, so 2 pi n. And then do the same thing for that second one. So 4 pi over 3 plus 2 pi n. Okay. Last 2 problems that are new. Number 5 is new from last time because we have both cosine and sine and they're being squared. That's not something that we can factor easily when there is a -1 involved. So we are going to graph this thing. So in your calculator, cosine squared, remember you have to put that squared after the fact. Subtract the other things over. You can also just move the cosine. It's going to give you the same type of answers. Not the same graph necessarily, but it will give you the same answers. Okay, if you move this the other direction, your graph will flip upside down. Going back to my 360. Looks like this. I'm going to go ahead and cut down my window again to the -2 and 2. That way we don't have a bunch of extra space. Okay, this time my solutions are showing up right at the minimum values. Again, if you subtracted the cosine, it would be at the maximum values instead. But I hope you're recognizing something that's going on here that's different than the others. There was nothing inside here that told us the period was changed. So we would assume our period is still 360 or 2 pi. But when we look at our graph, that's not the case. Because here's 360, but in 360 degrees, I've completed a maximum multiple times. Okay, I've done 1 lap and then a whole nother one. So my period is actually 180 here. And that's going to be nice to recognize. Because in general, we don't want to keep going forever and ever with solutions. We don't want to use any window. We want to use one period so that when we're generalizing it, we're doing it in the best way possible. Okay? So with that in mind, we're going to just find this 1, because if I change my window to 180, that's the only one that occurs, okay, in this 1 lap. And it looks like it's right at the halfway point. So I'm just going to trace, and it looks like right at 90 is the case. And so then that would look like pi over 2. And my period from the graph was 180. So I'm going to say plus pi n, where n is an integer. Okay? I'm going to let you pause the video and try that last problem, and then we'll check them together. This is another graph where you may want to adjust the window. Okay? When we talk about this equation, the period could be 180, or it could be 360. So we're going to start with the larger one. And when we look at the larger one, 360, I'm not seeing a repeat. So based on that, this would have to be the period. I'll adjust that out again so you can see it. 720. That graph repeats after that 360. I also changed the numbers from -5 to 5 just to give a little bit of room. We've got this 2 value of a stretch that's going on here. Now we want to find solutions back in the 180, and there were 2. So second trace, intersection. That was 270 degrees. And the first one, I believe, was at 90 degrees. Good. Okay. And because there's no pattern with 2, we're just going to stack them on top of each other. And I do want to show you with this graph, Because our period ended up being 360, this really does apply back to unit circle. 90 and 270 are equally distanced. And if you look at multiple periods, we can see that the space between all of those intersections is equal. Okay, but you wouldn't necessarily know that just by looking at it. So with two answers here, I want you to stack them on top of each other and add the period, which we decided was 2 pi. If you had pi over 2 plus pi n and not that one, great, but usually that is not something that you can do with these types of problems. Okay? I want to point out something before I set you free here. I picked on a couple problems just to give you a heads up on the homework. In theory, every single one of the problems we've worked with, you could solve by graphing, but I do expect that when you see a regular sine, cosine, or tangent, nothing squared, and there's no coefficient in front of your variable, I do expect you to still draw a picture and do those by hand, because honestly, it's going to be faster. Here's what I mean by that. For number 1, cosine is negative in these two quadrants. This negative 0.8 is not a nice triangle, so all we have to do is find the inverse cosine of negative 0.8. That angle is not nice in degrees, which means if you were to graph this, and I'm going to show you just so you have an idea of what to look out for here. If you were to graph this and move it over and do your intersections, you're not going to see nice numbers come out anyway. We're going to see this ugly decimal, just like we do when we work with the inverse, and you're still going to have to convert that to radians. It's much faster to just do the inverse cosine and change that number to radians right there in your calculator. Okay, so do these ones by hand. On the test, I'll have a spot where you have to solve some algebraically. Okay, remember with cosine, you just do positive and negative. You'll get ugly decimals for your answers and then generalize. The same thing goes for problems that you can factor easily. So if you are not someone who has a strength with brownie-based factoring, no problem. You can graph those now. But this one right here is an example that could be easily factored because it's not a trinomial. There are not 3 terms. So the only thing you have to do to factor this one is factor out a GCF. And there was one like this on last time's homework that caused some people some problems because we forgot common factor is a thing. Okay, but then from there, you have 2 options. Sine could be a 0, or sine could be a negative 1/2, and that's something we can draw a picture for, 0, 0, negative 1/2, negative 1/2, to answer the questions. Okay, so some by algebra, and then the new ones by graphing when you've got an a value or multiple functions. Okay, please come see me if you do struggle on any of these problems on the homework. I'm glad to help.